This lecture is part of a series of talks on modular forms. So in a previous lecture we talked about Hecke operators for modular functions, and what we're going to do now is discuss Hecke operators for modular forms. So modular functions are just the modular forms of weight 0, so now we're going to do the case of non-zero weight. So let's just recall what happened for modular functions. So we defined Hecke operators Tn for every positive integer n, and I'm just going to do the case T2 so I can write everything out explicitly. And there were three ways of doing this. First of all, we could take f of 2 tau and make this invariant under SL2z, which involves taking f of 2 tau plus f of tau over 2 plus f of tau plus 1 over 2. The second method was to take sum over lattices of index 2 of the lattice 1 tau, and you remember there were three sublattices which gave three terms which corresponded to 2 tau, tau over 2 and tau plus 1 over 2. Third way was to sum over all matrices of determinant 2, except we take cosets with the matrices of determinant 1 to make this a finite sum. And there are three coset representatives, 2, 0, 0, 1, 1, 0, 0, 2, and 1, 1, 0, 2, which again correspond to the three terms in the first case. Now, suppose we want to use weight k greater than 0, we do something very similar, except instead of working with an invariant function f, we work with an invariant form f of tau times d tau to the k over 2. And this causes, this factor of d tau to the k over 2 just causes some extra constants in all the formulas. For example, instead of taking f of 2 tau plus f of tau over 2 plus f of tau plus 1 over 2, we now have to take f of 2 tau times d2 tau to the k over 2 plus f of tau over 2 times d tau over 2 to the k over 2 plus f of tau plus 1 over 2 times d tau plus 1 over 2 to the k over 2. And if we expand out the d taus and the d tau over 2s and so on, this becomes 2 to the k over 2 times f of 2 tau plus 2 to the minus k over 2 times f of tau over 2 plus 2 to the minus k over 2 times f of tau plus 1 over 2, all multiplied by d tau to the k over 2. So you see the effect of putting in the d tau to the k over 2 is that we get all these powers of 2 turning up in odd places. Of course, we can do the same thing replacing 2 by any integer n, and what happens if we work out the details of this is if we have a function f of tau which is, say, sum of cm times q to the m, what we do, that the Hecke operator is given by the sum of things f of a tau plus b over d, where a, b, 0, d has the properties that a, d is equal to n. We're looking at the Hecke operator Tn, and 0 is less than or equal to b is less than d, because this was a set of coset representatives for determinant n matrices. And it's not too difficult to work out what this does to the Fourier expansion. The answer you get is that Tnf of tau is equal to sum over m of q to the m times sum d divides mn d to the k minus 1 cmn over d squared. So this is pretty much like the formula we had for the Hecke operator applied to modular functions, except we've got extra powers of d to the power of k lying around there. So let's look at this in a few special cases. Suppose we just look at the Hecke operator T2 applied to f. So if f is equal to c0 plus c1q plus c2q squared and so on, then T2f is equal to c0 plus 2 to the k minus 1 c0 plus c2 times q plus c4 plus 2 to the k minus 1 c1 all times q squared, and so on. And what we're going to do now is to just study this for the discriminant form delta. So you remember delta was equal to q times the product of 1 minus q to the n to the 24. And it's a cusp form of weight 12, and the space of these is one-dimensional, spanned by the discriminant delta. So delta is an eigenfunction of all the Hecke operators Tn, because each Tn takes cusp forms of weight 12 to cusp forms of weight 12, and the space of that is just one-dimensional. And let's see what the consequences of delta being an eigenfunction are. So let's write out the expansion of delta. So delta of tau is equal to q minus 24q squared plus 252q cubed minus 1472q to the 4 plus 4830q to the 5 minus 6048q to the 6. And you probably haven't noticed that minus 224 times 252 is equal to minus 6048. So there are some slightly unexpected relations between the coefficients. So these are the coefficients of q squared, q cubed, and q to the 6. And let's explain this using Hecke operators. Well, first of all, we notice that Tn of delta is equal to tau n times q to the 1 plus something or other. If you look at the expansion of Tn of something, here the numbers tau n are the coefficients of delta. So you remember this is tau 1, this is tau 2, and so on. This is tau 3. The notation comes from Ramanujan. So the eigenvector, so the eigenvalue of Tn on delta is just tau n, the coefficient of q to the n. And now we notice that Tm times Tn is equal to Tmn whenever m and n are co-prime. This is because Tm is a sum over lattices of index m, and Tn is a sum over lattices of index n. And if you've got a lattice of index mn, so if we've got a lattice m contained in L, this means that L over m is an abelian group of order m times n. Now, since m and n are co-prime, this lattice has exactly one subgroup of index n and exactly one subgroup of index m, which means that any sublattice of index mn can be sort of written uniquely by first taking a sublattice of index m, then a sublattice of index n. Here we're using the fact that m and n are co-prime. So by thinking of the Tm's as being sums over some sublattices, we get this property here. And since the eigenvalue of Tn is just tau n, this immediately shows that tau m times tau n is equal to tau mn, because tau 1 is equal to 1. So this explains why tau 2 times tau 3 is equal to tau 6. Of course, you notice that tau 4 is not equal to tau 2 squared, so something a little bit more complicated is going on when m and n are not co-prime. So now let's look at this. So let's write out T2 of delta explicitly. So we've got T2 of q plus T4, tau 4, plus 2 to the 11 tau 1 times q squared plus tau 6 q cubed plus tau to the 8, tau of 8, plus 2 to the 11 tau 2 times q to the 4, and so on. And if we look at delta, we see this is just tau 1 of q plus tau 2 of q squared plus tau 3 of q cubed plus tau 4 of q to the 4. And now we notice that tau 2 of delta is a multiple of delta, and it's obviously obtained by just multiplying by tau of 2, because you can see that by looking at the coefficient of q. So now if we look at the coefficient of q squared, we see that tau 2 squared is equal to tau 4 plus 2 to the 11 tau 1. And let's just check this. That says 24 squared is equal to minus 1472 plus 2 to the 11 times 1. And more generally, we get the relation tau 2 times tau of 2 to the n is equal to tau of 2 to the n plus 1 plus 2 to the 11 tau of 2 to the n minus 1. This is by looking at the coefficient of q to the 2 to the n in these two relations. Of course, there's nothing special about the prime number 2. We find that tau of p times tau of p to the n is equal to tau of p to the n plus 1 times, plus p to the 11 times tau of p to the n minus 1. So just as you remember, for the elliptic modular function, we found that by applying all the Hecke operators to it, we got some complicated nonlinear relations between its coefficients. And for the discriminant function, we've also got some complicated nonlinear relations between its coefficients. For the elliptic modular function, we found a neat way to encode all these relations was as a sort of infinite product. And it turns out you can do the same for the discriminant function, except the infinite product is a rather different sort of infinite product. In fact, it turns out to be an Euler product. So here's what you do. What we do is we take the Mellin transform of the discriminant function. So we integrate delta of I tau times it times t to the s minus 1 dt. That's a Mellin transform. And now using the fact the integral from 0 to infinity of e to the 2 pi I n I t times t to the s minus 1 dt is just 2 pi to the minus s gamma s over n to the s. That's just the more or less the definition of the gamma function. We find this Mellin transform of the discriminant is 2 pi to the minus s times gamma of s times sum over all n of tau n over n to the s. So we've turned the discriminant function into a Dirichlet series if you ignore this gamma function, the 2 pi to the minus s. So we can call this bit here L of s. And this whole thing, let's call it L star of s. So L star of s is just L of s multiplied by gamma factor in a power of 2 pi. And now we can turn things we know about the discriminant delta into properties of L of s. For example, the discriminant delta is a modular form, so delta of minus 1 over tau is equal to tau to the 12 times delta of tau. If you substitute this into the Mellin transform, you find L star of 12 minus s is equal to L star of s. And you notice this is very much like what happened for the Riemann zeta function. So if we put zeta star of s is equal to pi to the minus s over 2 times gamma of s over 2 times zeta of s, then we have zeta star of 1 minus s is equal to zeta star of s, which is the functional equation for the Riemann zeta function. So it's sort of just like this. Incidentally, you know that zeta function is a critical line, and with real part s equals a half, and the Riemann hypothesis says that all the non-trivial zeros lie on this line. And there's a similar conjecture for this funny L series. Its critical line is now the s with real part 6, and there's a conjecture that all the non-trivial zeros have real part 6, and so on. Actually, the Mellin transform for this is better than the one for the Riemann zeta function, because this vanishes at the cusp, so this converges for all s, and this L function doesn't end up with any poles. Anyway, you all remember the zeta function has this infinite product over all primes of 1 over 1 minus p to the minus s. And all those funny relations we found between the coefficients of the delta function can be expressed as an Euler product for L of S. So we put L of S, which is sum over tau of n over n to the s, and using the fact that tau of mn is equal to tau m times tau of n whenever m and n are co-prime, we can write this as a product over all primes of 1 over p to the 0 plus tau of p over p to the s plus tau of p squared over p to the 2s, and so on. And now, using the relations relating tau of p to the n, we can write this as a product over all primes of 1 over 1 minus tau of p times p to the minus s plus p to the 11 times p to the minus 2s. So you see the equality of these two just follows from the fact that 1 times tau of p to the n plus 1 minus tau of p times tau of p to the n plus p to the 11 times tau of p to the n minus 1 is equal to 0. And you see the numbers 1 and tau of p and p to the 11 appearing in this recursion relation are exactly these coefficients here, which is what you need to show that these two expressions are the same. This L series constructed from the Ramanujan's tau function is indeed very similar to the Riemann zeta function. It's got an Euler product, a Riemann hypothesis, and so on. So that there's a famous conjecture due to Ramanujan about this function that if you look at this expression 1 minus tau p, p to minus s plus p to the 11, p to the minus 2s, you notice it's really a sort of polynomial 1 minus tau of p times x plus p to the 11 times x squared. And Ramanujan conjectured that the roots of this are complex. They're complex conjugates. This is equivalent to saying that tau of p is less than or equal to 2p to the 11 over 2 if you work out the condition for the roots of this to be complex. So this is the Ramanujan conjecture, which was a very famous conjecture until it was finally proved by Deligne in one of the really spectacular piece of mathematics. Deligne first reduced this to the Weil conjectures for zeta functions over finite fields, and then proved the Weil conjectures, and as a result managed to deduce this very deep inequality. A consequence of this is that tau of n for all n is at most n to the 11 over 2 times sigma 0 of n. I'll just finish by showing you Ramanujan's original paper where he introduced his conjecture. So if you look here, you can see this is Ramanujan's paper on certain arithmetical functions, and here you can see he's calculated a table of the function tau of n, and down here he's stating his conjectures. He says it appears that sum of tau n over n to the t is given by this infinite product. So he's basically conjecturing all the relations you get from the Hecke operators. These conjectures were proved by Modular a year or two later. And here he's conjecturing the Ramanujan conjecture, which is here. And he points out as a consequence of it that tau of n is at most n to the 11 over 2 times the number of divisors of n. If you want an exercise, if you look at weight 12, 16, 18, 20, 22 or 26, notice that for all of these the space of cusp forms is one-dimensional, so it's spanned by delta or delta E4 or delta E6 or delta E8 or delta E10 or delta E14. And as an exercise, you can try and find analogues of Ramanujan's work on the discriminant function for all these other functions here.